Hi, this is Rob Bolaños. Welcome to the analysis and design of a flyback. This is going to be video 29. Uh, what I'm going to do is I'm going to do a second design example. And the reason I'm doing this is uh, I get emails from students requesting uh, different voltages and currents and so forth. And the example that I have been using is a low power, basically 6 watts, and I'm in simulating only one output. So in this case, I'm going to go ahead and use a little bit higher power. Okay, and it's going to be multiple outputs. So I don't think I've expressed how to handle multiple outputs. So I'm going to go ahead and show the procedure that you can use. Now, as you learn more on flyback design or power supply design, you can develop your own procedure. But this is, I guess, a simplified procedure that you can use. Okay, so here are the specifications. This one is a 2 multiple outputs. I may add a V3 and close it, so I'll show you the difference. But in this case, we're going to go with 12 volts, 4 amps. Okay, so that's going to be 48 watts. And then 5 amps at 10, so that's 50 watts. And the efficiency that one of the students was that they had spec was 85%. Now for a flyback, this may or may not be doable. Usually you'd be lucky if you can get somewhere in the 70%, 75%, maybe to low 80s. Typically if you want to go 85, you may have to use synchronous rectification. Okay, if you don't know what synchronous rectification, you may want to go to the forward converter playlist. I have a video there explaining what synchronous rectification is. Okay, continuing, the frequency is 40 kilohertz. Okay, and all the previous I've been using 100 kilohertz, so we'll go ahead and change it to 40 kilohertz. And then I have been using previously I believe 22 or 24 volts. Okay, so this is more this would be the DC after you filter it from an AC. Okay, so this is basically the range. So the minimum voltage range DC, this is one of the design parameters that I'll be using. Okay, so I'm going to call that VN minimum. Okay, so we have that. So I think we have, this is the bare minimum specs. For now, we haven't included ripple, but we can do the ripple later on. Let me go ahead and put bare min. Okay, so we'll go ahead and go with the design procedure. Okay, so the first step that you want to do is you want to add up your total power. Okay, so in this case we already calculated up there. This is supposed to be, the first one is 12 times 4 amps. You got 48 watts. And then your second output is 5 at 10, that's 50. So the total output power is 98 watts. Okay, so that's the first step that you want to do. Then you want to convert that from the output, you're going to convert it to the input. Okay. So the way you do that is you divide this, and let me go ahead make let me write the real equation. So this is going to be P output efficiency. Okay, so in this case it was, what was it, 80 or 98 watts. And even though this is not probably a doable efficiency, let's go ahead and just use it for right now. So it's 98 divided by 0.85, 115.3 watts. Okay. So then, once you have the input power, from that you can find the average current or the average input current, and that's basically your input power, which we already calculated, divided by your minimum voltage. So we have these two here. So this is the average. Okay. So basically, if you have your power supply, this is your power supply, and of course you have your 12 volts and your 5 volts coming out, and then you're gonna have, this is connected to your 85 volts. If you put a current meter here and you put a meter here, you're gonna get the average right there. That's what you're gonna read. Okay, if you do a current meter, okay, so that's what you would get. Okay, so once you have that, then there's a relationship that if you know what the average power, you can calculate what the peak, or at least get an estimate. So basically you want to find the peak current. Okay, so this peak current, that's at the primary, and that would be the primary of the L pri, or the primary inductance. And also flows through MOSFETs. Anyway, so it's the I average divided by 0.5 times the duty cycle. Okay, so let me talk a little bit about the duty cycle. Duty cycle, you can be anywhere from 0.4 to 0.45. Okay, so this depends on your PWM. So you have to look at the data sheet. And you need to look what is the minimum duty cycle. So it may have a minimum of let's say 46, something like that. So if you want enough margin, you pick something a little bit lower. So you may pick 42. But in this case, for this design example, I'm going to go ahead and give me a hefty margin. I'm going to use the most conservative, which is this. Okay, 0.4. So that's what I use here. So I'm just going to say that most conservative. Okay, so here's the peak current. So now once we have that, then you can calculate the primary of your flyback transformer. that is calculated by your VN minimum, the duty cycle, your peak, and the frequency. So we said that the frequency is 40 kilohertz, which is right there. So here we entered the parameters, and we end up with 125 microhenry. So that is the inductance that we would expect on the primary. Okay. So then once we have that, then the next step is you want to calculate the turns ratio of your secondaries. And you can use this equation. Actually, this equation is actually, let's say NR is the turns ratio, and it's basically going to be V out of the source, and this is going to be Vn min. Okay, so this is for the 12 volts, and this is for the 5 volts. So we divide both, and these are the turns ratio. So these numbers are not the actual turns ratio, but they're the SPICE turns ratio. Okay, so that's the SPICE turns ratio. So these are the numbers that you're going to be using. Okay, so then the next thing that you want to do is you want to calculate the current sense resistor. So for this example, instead of using a current transformer, I'm going to go ahead and use a current sense resistor, just to make the simulation easier. Okay, so in this case, you want to set this is the voltage. Basically, this comes from your data sheet, your PWM data sheet. And you want to look under the current limit spec. It'll say that the current limit will be limited when V I lim, they call it, of 1 volt. So basically, you're going to have a chip, and there'll be a CS, or current set. Okay, so remember, the current is going to look something like this. Okay, it's going to be a voltage. So this is 0 volts, and this triggers a comparator. Okay, this comparator triggers at 1 volt. Okay, so you want a little bit of a margin. Okay, you don't want to set this exactly to 1 volt, the peak of this. You don't want the peak to be 1 volt. You want to set it a little bit high, lower. So instead, remember, this is the limit, 1 volt, and you want to set it somewhere about 0.8. So in other words, you want this current to look something like this. Okay, so this area, that's your margin. Okay, and since we're setting this to 0.8, this 0.2 is really, you're giving yourself actually 20% margin. What does that mean? Well, let's say that the total output, let's say I out, And let's say let's say that this was a let's say we had a single supply, and it's the 5 volts at 10 amps. Okay, so that means that when you hit the 0.8 volts, that means that you're going to have 10 amps in your output. Okay, so for it to travel all the way up to the 1%, that means that this will trigger at 12 amps. So 12 amps is where the current limit will trigger. So that's the margin. So anyway, so all of this is just to explain why I picked this 0.8. Anyway, so you got 0.8, you divide it by the peak current, and you have 0.117. Okay. And do we have anything else? I think that's it. Okay. So now we can go ahead and try to do a simple simulation. Okay. So we can come up here. Let me go ahead and take this off. I think it will still work. Okay, so let me backtrack a little bit. Okay, I will be using Basso's PWM. Okay, and one thing that we need to calculate is TP, or the period. So in this case, it's 1 over the frequency. That would be 25 microseconds. Okay, so this, we can define it when we double click on the PWM. Okay, so we double click, and it says PWM CM is current mode 2, and we type in period, and period equals 25U. Okay, so now with this tells, basically sets the frequency that the PWM will be oscillating. Okay. Okay, so now we have our transformer, and if you notice, L1 is the primary. Oh, and what I want to point out, look at the dots. The dots are very important. You want the dots to be out of phase. So this is on top, and here is on the bottom. Okay, so you want them out of phase. Okay, so here I'm using the curly brackets, and I define LP and close curly brackets. Curly brackets is a parameter, and I can define LP, and I do that by basically, you go to the text and you put dot param, and then LP equals 125U. Okay, so that's basically how you define these parameters. Just use the text. Okay, so now I'm going to define the turns ratio, and remember I said that we calculated what the turns ratio, and we're going to use that for the spice. So here's the two numbers, 0.141 and 0.04558. So here is NR1 0.117, NR2 0.058. Okay, so this is the turns ratio of the 12, and this is the turns ratio of the 5. Okay, so if we look here, we have L2. L2 is defined as curly brackets NR1 times NR1 times LP. So if you type that in here, then by defining this, we'll calculate the output inductance of the secondary of this particular one, and it does it with this formula. So all you have to do is define your LP, which is here, and then the turns ratio, and it does it automatically. Okay. And then you have your diode, capacitor, and your load. Okay. So now what we want to do is we added a second winding, and the way you do that is very simple. All you have to do is copy this part, right? You copy it, and then you paste it, and that's what I did right here. I pasted on the side, and I changed these so they won't be connected. So this one is VSEC, this is VSEC 1, and then I named this Vout 2, and this is Vout 1. Okay, so now this is L3. Okay, this has to be coupled to this, and this L2 has to be coupled to the primary. So how do I do that? Well, you do that with the K factor. So basically you can type in insert, you put a K, and that's it. Okay, so once you have the K symbol there, then you have to tell what you want to couple. So in this case, the first line, when you double click, if you notice it says L1 is coupled to L2, and it's coupled to L3. Okay, so this tells me, or it tells SPICE, that these three are coupled to each other. Okay, L1, L2, and L3 are coupled. Okay, and then I want to mention that there's a 1 here. Okay, this number represents the coupling coefficient. Okay, this tells the inductor how well it couples. So when you put a 1, it means that you have 100% coupling coefficient. Okay, so in reality you never get perfection, so you might end up with a 0.09998. Okay, still good coupling, but there's some windings that they're not perfectly coupled. But in this case, we're just going to go ahead and make it a perfect coupling, just for right now, just to simplify things. Okay, so then we set it to 1. Now we have both windings defined here. I have my loads defined. 12 divided by 4 is 3, and then 5 divided by 10 is 0.5. So we have that there, and I believe I have everything. Okay, so now go ahead, press run. Oh, and I forgot to mention, and then I can set the current sense resistor here, which we had calculated 0.117. 0.117. Okay, we can define it right here by setting it to 0.117. So it's running a simulation, and then we'll compare, see how close we got. And mind you, I'm using a PWM, so this will close. And if you notice, here's the output. Okay, let me go ahead and eliminate this. Okay, so you have a little bit of overshoot. So let's put the cursor here. And it's 12 volts. Okay, so then bring it down here, and this one's 5.509. Okay, so that's pretty good. Okay, so let's check some other stuff. We had calculated Okay, let's go back. Let's see how well we calculated things. We had mentioned that the peak current was going to be close to 6.78. Okay, this peak current is a current flowing through L1. Okay, so here I define a statement to plot the current through L1, which is this one. So it should be close to the 6.78 that we calculated. And if we look for IL1, here it is. Okay, so we click and let's see how close. 7.18, not that bad. Okay, so it's in the ballpark. Okay, let's look for something else, another check. Okay, let's see how close did we get. Did we set the R cents? Basically we want V cents to be close to 0.8 volts. Okay, so if we go here, V cents, and we can define that by right here, I cents. That node is named I cents, and here I put a plot, auto plot directive trans, basically plot the voltage at node I cents. Okay, so that is here. Okay, and you can tell that it's close to it. It's 0.750 millivolts, so we have quite a bit of margin. Okay, so 1 volt is over here, so we have this much from here to here of margin. Okay, so that's good. So this is one way to do a multiple output. Now what I want to do one more thing before I go ahead and end this lecture, that here I am closing on the secondary, and typically in this case the ground of the primary is the same as the ground in the secondary, and typically you would use an opto here. Okay, because this you can power it from the primary, but let's say you add a third winding and you close to the third winding. Okay, how would you do that? Okay, so what we can do is, again, we can copy this. Let's add a third winding. Okay, we'll add it there. And what I'm going to do is, instead of closing on this, I'm going to go ahead and close on this one. And sometimes they call this the auxiliary winding. Okay, and let's get rid of this K parameter. And now let's couple it. So now this is L4. So all I have to do is go to K1, type in L4, and that should couple it. Okay. So now this winding is a third winding, and you can close on this But this could be referenced to the primary, while these are referenced to the secondary. Okay, doesn't make sense here, but in the next lecture I'll split up the grounds and maybe even do an opto so you can see the difference. Okay, so let's go ahead and do this, and let's do one more thing. And let's lightly load this. Let's say that's 500, which should be a light load. Okay, so this is going to be 12 volts as well. So let's make this L3. Okay. L3. Okay. So I believe, let's see if it'll run. Hopefully I didn't do any mistakes, and it looks like it did. And let's see, what did I do? This is current loop on 4. Oh, see this VSEC? VSEC, that means that they're connected together. Okay, so I can go ahead and delete it. So now the regulation is done, or I'm closing on the third. Instead of the first, I'm closing on the third winding. And depending on how close your coupling is, they may track closer or they may not. It all depends on the coupling. Okay, so you notice, see, this is what I want to show. See, this doesn't have a lot of load, but then the outputs are sagging. Okay, so let's see if I let it run a little longer. Will it reach an equilibrium? It may or may not reach equilibrium, but I'm curious to find out. So this is actually pulsing quite a bit of power, and this is hardly any power. And this is one of the disadvantages, that if you have uneven power or currents, the flyback doesn't regulate as well, or cross regulation is not as good. And in fact, you may have to put more load here to make it regulate better. So the duty cycle actually goes down, and it doesn't allow it to, because it's closed on this one. See, so that's very interesting. So let's go ahead and see. So basically, since this is lightly loaded, the PWM is reducing the pulse width to a bare minimum, and it's starving these windings. Okay. Okay, so it looks right here. I put a little bit more of current, and it looks like it's adjusting. Okay, so just run it a little longer. Let's say 15. This may take a long time, but I'm curious. And this is one of the reasons where you can use an opto and actually feed and actually close on the primary and then feed that back. Another option would be to place the PWM on the secondary side, but then you would have to use a housekeeper supply to derive secondary voltages to power your PWM. So I may show that in the next lecture, but for the time being, I want to see how this works. I'll go ahead and stop it at 10 and take a sneak peek. See if it's going in the right direction, or it may have some instability since I haven't changed the compensation. So let's see what happens there. Actually, see, they are climbing up. Say it's recovering. Okay, so okay, let's try that. Okay, there you go. It looks like it recovered. It may have recovered even with a lower current. I just probably had to run the simulation. But here you have it. Basically, the voltages are on top of each other. Here's the 12 volts on the first and the third supply, and then you have the 5 volts on the second supply. So this is one way of doing a third. Okay, I'm gonna go ahead and stop here. This is quite a bit of information. I'm gonna go ahead and see if I can refine it a little bit. And piece of information I want to pass on, that if you are a university student, you qualify for a 50% off of the Penzar simulation package. You have to show proof that you are a student, and if you mention my name, you'll get the 50% off. And if you are not a student and you are a practicing engineer, if you mention my name, you can get 10% discount off of the price. Again, I get no commission. I don't get compensated or anything, but it's one of the little things that I was able to get for you guys in case you're interested in getting a simulation package with the SPICE models. Anyway, if you have any questions, email me at rbola35618. Subscribe, ring the bell, and like. If like I said, if you have any questions, email me or post them on my channel. Thank you for watching.